You're driving on the highway when your manual transmission jams between gears. The engine screams at redline going uphill. Drop to a lower gear and it bogs down, gasping for power. You're burning fuel, losing speed, and there is no way to match the engine to the road. Fixed pitch propellers did exactly this to aircraft in the 1930s. One blade angle for all conditions meant wasting power at every altitude and airspeed. Climb too steep and the engine over-revved into destruction. Level off and it bogged down, choking on its own resistance. British pilots in 1940 needed every advantage against the Luftwaffe, but their Spitfires and Hurricanes were stuck in the wrong gear half the time. Hamilton Standard, an American manufacturer in the industrial Midwest, had already solved it. A governor that automatically adjusted blade pitch to keep the engine in its power band. The constant speed propeller became the automatic transmission of the sky, and it changed air power forever. Picture an RAF test pilot in 1937 climbing through 15,000 feet in a Hurricane prototype at Martlesham Heath. The Rolls-Royce Merlin engine produces 1,030 horsepower at sea level, but up here the air thins and everything changes. His propeller, 2 tons of shaped duralumin spinning at 2,600 revolutions per minute, is locked at a fixed pitch angle, set for optimal thrust during takeoff. At altitude, those blades bite into rarefied air like a gear too low for highway speed. The engine over-revs, revolutions per minute climb dangerously toward 3,200, and the pilot must reduce throttle to prevent mechanical destruction. He is flying a 1,000 horsepower engine at 3/4 power because the propeller cannot adapt. Back at the airfield, engineers from Hawker and Supermarine knew the brutal math. Fixed pitch meant choosing between climb performance and level flight speed, optimize for one and sacrifice the other. Every sortie became a compromise, and in 1938, with war approaching, compromise meant casualties. RAF fighter squadrons needed aircraft that could climb fast to intercept altitude, cruise efficiently on patrol, and dive without destroying themselves. Fixed pitch propellers could not do all three. Why does altitude feel like losing a gear? Because aerodynamically, it is, and there is no clutch to save you. The physics were unforgiving. A propeller is a rotating wing, and like any wing, it generates lift, except the propeller calls it thrust and generates it thousands of times per minute. Blade angle, called pitch, determines how much air the propeller bites with each rotation, and that angle must match the aerodynamic load or the system fails catastrophically. Too fine an angle at low speed, and the engine spins freely, producing some thrust but over-revving into danger. Valves float, connecting rods stretch, crankshafts twist beyond elastic limits. Too coarse at high speed, and the engine lugs against excessive resistance, like a car stuck in high gear from a standstill. Combustion temperatures spike, detonation begins, and pistons fail. In 1937, aerodynamicists at the Royal Aircraft Establishment in Farnborough ran wind tunnel tests measuring torque curves versus air density at simulated altitudes up to 40,000 feet. Their findings confirmed what pilots already knew from harsh experience. Revolutions per minute must track changing aerodynamic resistance, or you are fighting the engine at every airspeed and altitude. Test crews documented the failure modes in clinical detail: over rev at altitude, bogged down at sea level, or some compromise that satisfied neither condition. Engine manufacturers issued operating limitations that restricted performance to safe margins, which meant capable engines were running at partial power. Can a propeller stall like a wing? Absolutely. When blade angle exceeds the critical angle of attack, airflow separates, thrust collapses, and you are not flying, you are falling with expensive machinery. By 1938, British factories were producing propellers with manually adjustable pitch, so pilots could change the blade angle in flight, using cockpit controls connected to mechanical actuators in the propeller hub. De Havilland and Rotol manufactured 2 position propellers that offered a coarse pitch for high-speed flight and a fine pitch for takeoff and climb. It was better than fixed pitch, but barely adequate. A pilot climbing into combat airspace had to manage throttle, mixture control, revolutions per minute, boost pressure, and blade pitch simultaneously while maintaining formation, watching for enemy aircraft, and monitoring fuel. The workload was staggering and dangerous. Manufacturing leads at de Havilland's factories in Hatfield knew that mechanical governors existed. Centrifugal speed regulators had controlled steam engines since James Watt's time, but adapting that principle to a propeller spinning at 3,000 revolutions per minute while handling 3-ton centrifugal loads and absorbing 1,000 horsepower of thrust across temperature swings from -40 to +200 degrees Fahrenheit demanded precision machining beyond most factories' capabilities at scale. Inspectors rejected propeller hubs with tolerance variations of a few thousandths of an inch because hydraulic seals failed and oil leaked, causing pitch control loss. The mechanical linkages had to be lightweight enough for aircraft use, fail-safe under combat damage, and simple enough for field maintenance by mechanics working in muddy pastures with basic tools. Manual controls proved too slow and risky. Pilots were adjusting pitch every 30 seconds during climbs, taking attention away from navigation and tactics. What if the engine adjusted itself automatically, leaving pilots free to fly and fight? That is when American engineers entered the conversation with a proven answer. Hamilton Standard, a division of United Aircraft Corporation based in Windsor Locks, Connecticut, had been developing constant speed propellers since 1935 under Chief Engineer Frank Caldwell. Caldwell understood the core problem with elegant simplicity. You needed a mechanical brain that sensed engine, RPM, and commanded blade angle changes fast enough to prevent over-revving or stalling, all while operating reliably under extreme conditions. The solution emerged from first principles, a flyweight governor that used the same centrifugal principle that regulated steam engines and industrial machinery, integrated directly into the propeller hub so it could respond instantly to speed changes. The concept was mechanically simple, but engineering it for aircraft use was brutally difficult. Picture the geometry. As engine RPM increased, small weighted arms mounted inside the spinning hub moved outward against calibrated spring pressure. That outward movement opened a valve controlling pressurized engine oil flow to a hydraulic piston machined into the propeller hub. The piston was mechanically linked to the blade shanks through a system of pins and collars. Oil pressure pushed the piston forward, rotating all blades simultaneously toward increased pitch. More pitch meant more aerodynamic load, which slowed the engine back toward the target RPM. The system hunted for equilibrium continuously, making micro adjustments dozens of times per minute as flight conditions changed. The engine stayed in its power band automatically, regardless of airspeed, altitude, or throttle setting. Set target RPM once, and the governor maintained it. How do spinning weights think? They do not. They react to centrifugal force with perfect mechanical consistency, which is better than thinking. Physics does not forget, does not get distracted, and does not make errors. The mechanism demanded precision that pushed manufacturing capabilities. Picture the propeller hub assembly in cross-section. Each blade root was seated in a roller bearing race, free to rotate through 30 degrees of pitch range, while a mechanical linkage constrained each root to a central hydraulic piston that moved all blades in unison. Engine oil, pressurized to 300 pounds per square inch by a dedicated gear pump driven off the engine accessory case, flowed through passages machined into the hollow propeller shaft. The channels had to be smooth enough to prevent turbulence that would cause pressure fluctuations, and the seals had to maintain pressure while the shaft spun at 3,000 revolutions per minute. The flyweight governor sat in the hub dome, a compact assembly of spring-loaded arms, pivots, and a pilot valve that controlled oil flow direction. When engine revolutions per minute exceeded the pilot's selected setting, for example 2,650 revolutions per minute for cruise flight, centrifugal force overcame spring tension, and the flyweights moved outward by perhaps a quarter inch, opening a valve that directed oil pressure behind the piston to increase blade pitch. The blades rotated toward course pitch, adding load, and engine speed dropped back toward the target. If engine speed fell below the target, spring pressure closed the valve, allowing oil to drain from the piston through a return passage, and pitch decreased toward fine. The whole cycle took less than a second. Test engineers at Hamilton Standard ran endurance trials at their facility in 1939. watching oil pressure gauges flicker rhythmically as the system responded to throttle changes, load variations, and simulated altitude conditions. They ran governors for 500 hours continuously, simulating months of combat operations. Why does oil beat cables and gears at 3,000 revolutions per minute? Because hydraulics do not stretch, do not bind, do not wear at joints, and do not fatigue. Oil is effectively incompressible, self-lubricating, and perfectly obedient to pressure. Reliability teams obsessed over failure modes because combat is the ultimate stress test. What happens when the system fails mid-dive with the engine screaming and the propeller unable to add pitch? Hamilton Standard engineers designed a fail-safe default that prioritized engine survival. If oil pressure dropped below 200 pounds per square inch, whether from pump failure, line rupture, seal degradation, or combat damage severing a hydraulic passage, calibrated springs in the hub assembly drove the blades toward coarse pitch automatically. Coarse pitch added maximum aerodynamic load, preventing over-rev and the catastrophic engine destruction that followed. A pilot could limp home on reduced power, manually managing throttle to avoid loading the engine so heavily that the propeller stalled and thrust collapsed. But the engine would not tear itself apart from overspeed. They tested this deliberately and repeatedly, cutting oil lines during full power test runs on ground test stands. Engineers watched tachometers as propellers at 3,000 revolutions per minute lost pressure. The blades rotated to full course within 2 seconds, and RPM stabilized below the red line at 2,400 revolutions per minute. The engine continued running. By late 1939, the U.S. Army Air Corps had accepted the hydromatic constant speed propeller for production aircraft after witnessing demonstrations at Wright Field in Dayton, Ohio. British Purchasing Commission observers, desperate for any technology that could improve fighter performance before war came, watched demonstration runs and immediately requested licensing rights for British manufacture. The Battle of Britain was months away, and RAF Fighter Command needed every technical advantage against the Luftwaffe's numerical superiority. Combat-safe automation was no longer experimental theory, it was operational necessity. The British placed orders for 5,000 units before a single propeller had seen combat. That is confidence born from desperation and engineering clarity combined. Transatlantic supply chains moved with wartime urgency in 1940. Packard Motor Car Company in Detroit, already producing Merlin engines under license from Rolls-Royce, licensed Hamilton Standard's patents and tooled up production lines for constant speed propellers. The challenge was not understanding the concept, it was achieving manufacturing tolerances at production scale. The propeller hub assembly contained 43 precision machined components that had to maintain hydraulic seals while spinning under 6-ton centrifugal loads across temperature extremes from Arctic patrols to North African desert operations. Packard production leads hired machinists from the automotive industry, experienced craftsmen who understood tolerances and production flow, but aircraft standards were categorically different from automotive work. A connecting rod tolerance acceptable in a car engine, perhaps 5/1000ths of an inch variation, would cause catastrophic seal failure in a propeller hub where oil pressure had to be maintained against centrifugal force trying to fling it outward. They scrapped entire production batches over variations measured in 10,000ths of an inch, tolerance limits invisible to naked eye inspection. Machinists learned to work to aircraft standards or found other employment. Quality control inspectors rejected hubs for surface finish imperfections that would not have warranted a second glance in automotive production. By September 1940, Packard was shipping 100 constant speed propeller assemblies per week across the Atlantic to Britain, each crated with protective Cosmoline coating and detailed installation instructions. Each unit underwent pressure testing to 400 pounds per square inch, dynamic balance verification on specialized rigs, and 20-hour endurance runs before acceptance. Can Detroit tolerances meet combat reality? Only if you redefine what Detroit tolerances mean and reject anything less than perfection. They did, and the rejection rate in the first 6 months exceeded 30%. It was expensive, but cheaper than losing aircraft to propeller failure. RAF pilots noticed the difference immediately and reported it with the understated Enthusiasm, typical of British fighter pilots facing mortal stakes. Squadron maintenance chiefs installing the new American propellers on Spitfire, Mark II aircraft at airfields across southern England in late 1940 reported that pilots stopped chasing the throttle, the constant manual adjustment of pitch and power settings that had defined combat flying and consumed attention needed for tactics and survival. A pilot climbing to intercept altitude at full throttle simply set the propeller control lever to maximum revolutions per minute for takeoff, then reduced it to a cruise setting at altitude. The governor handled everything else automatically and invisibly. Takeoff rolls shortened by 15% because the propeller maintained optimal bite throughout acceleration instead of compromising between static thrust and climbing thrust. Climb rates increased dramatically because the engine could deliver full power continuously without the pilot backing off throttle to prevent over-reverent dive. Performance improved because increasing airspeed automatically increased blade pitch through the governor's action, preventing the destructive overspeed that had previously limited dive angles and pursuit tactics. Test pilots at the Aeroplane and Armament Experimental Establishment at Boscombe Down in Wiltshire flew systematic comparison trials in early 1941. Same aircraft type, same engine variant, same fuel load, different propellers. A Spitfire Mark II with a fixed pitch propeller climbed at 2,100 feet per minute at sea level and 1,650 feet per minute at 15,000 feet. The identical aircraft with a constant speed propeller climbed at 2,650 feet per minute at sea level and 2,200 feet per minute at 15,000 feet. That is 26% more climb performance at sea level and 33% more at altitude with zero additional horsepower, no engine modifications, no airframe changes. Think about that transformation. The same engine pulling harder, going faster, climbing steeper, just by matching the propeller blade angle to the work being demanded. The power was always there. They had just been wasting it. Flight test officers documented the performance transformation with the clinical precision that turns engineering claims into operational doctrine. The power utilization curve, a plot of effective thrust horsepower versus indicated airspeed, showed the difference with brutal clarity. Fixed pitch propellers had a narrow efficiency peak, typically around a single design airspeed. Operate outside that speed range by even 30 miles per hour, and you wasted power to aerodynamic mismatch between blade angle and airflow. Constant speed propellers maintained near peak efficiency across the entire flight envelope from takeoff to maximum speed. The data was irrefutable. At 15,000 feet, a Spitfire with a fixed pitch propeller delivered 850 shaft horsepower to the propeller and achieved 320 miles per hour in level flight. The same aircraft with a constant speed propeller delivered 850 shaft horsepower and achieved 355 miles per hour, 35 miles per hour faster from the same power. How do you get speed without adding power? You stop wasting it to inefficiency. Every horsepower converted efficiently to thrust instead of being lost to turbulence, vibration, or blade stall, translated directly to performance. The Royal Air Force published comparative trials in restricted technical bulletins that circulated among engineering staffs and procurement officers. American manufacturers read them and accelerated production schedules. By mid-1941, constant speed propellers were standard equipment on every new fighter, bomber, and transport entering service with the U.S. Army Air Forces and the RAF. The technology had proven itself in the ultimate laboratory, combat over the Channel and the North Sea, where performance margins measured in seconds of climb time or miles per hour of speed determined who survived and who did not. Fighter Command calculated that the constant speed propeller reduced time to altitude enough to allow squadrons to intercept bomber formations 2 minutes earlier than previously possible. 2 minutes at 250 miles per hour is 8 miles, the difference between intercepting bombers before they reached London or watching them drop their loads and turn for home. Engineers kept improving the system because good engineering never stops at good enough. In 1942, propeller designers at Hamilton Standard and Curtiss-Wright added feathering capability. They could rotate blades to a full 90-degree angle, aligned edge-on with the airflow like a weather vane. Picture a twin-engine bomber, perhaps a B-25 Mitchell, losing an engine to combat damage over occupied Europe. A windmilling propeller on the dead engine, blades spinning freely in the airflow without power, creates enormous parasitic drag, often exceeding 1,500 pounds of force, like deploying a parachute asymmetrically from one wing. The aircraft yaws violently toward the dead engine, loses altitude at 500 feet per minute, and becomes nearly uncontrollable. Pilots fought the asymmetric thrust with full rudder deflection and maximum power on the good engine, exhausting themselves and burning fuel at unsustainable rates. With feathering capability, the pilot pressed a button that drove the failed engine's propeller blades to full course pitch and then beyond, rotating them 90 degrees to their stops. Blade edges faced the airflow. Drag dropped to nearly zero, perhaps 50 pounds of residual drag from the hub. Suddenly, flying on one engine became survivable instead of catastrophic. Safety boards documented dozens of bomber crews making it home across hundreds of miles of ocean or enemy territory on one engine after feathering the damaged propeller. The mechanism was mechanically simple. An additional detent in the pitch control linkage drove the blades to their coarsest possible position using spring pressure and a high-pressure oil shot from an accumulator. It used the same hydraulic system, the same governor architecture, just extended to a new mechanical limit. Why does turning the prop sideways save lives? Because drag kills altitude, and altitude is survival time. Feathering eliminated the drag and gave crews the time they needed to reach friendly territory. High altitude operations pushed the technology into new extremes. Supermarines engineers developing the Spitfire Mark IX for service in 1943 faced a new challenge. The Merlin 61 engine used a two-stage, two-speed supercharger that delivered full power up to 30,000 feet by compressing the thin air to sea level density. But air density at that altitude was one-third of sea level, and aerodynamic forces on the propeller blades changed dramatically. The constant speed governor had to coordinate with the supercharger's automatic boost control system, maintaining target RPM, while the engine's effective power output changed with altitude and the propeller's aerodynamic loading changed with air density. They could not simply use the same governor calibration from low-altitude engines. The system would hunt unstably, surging between fine and coarse pitch as it tried to compensate for the changing conditions. Hamilton Standard engineers added a barometric compensator to the governor assembly, a small aneroid capsule, the same principle used in altimeters that sensed ambient air pressure and adjusted the governor's spring tension accordingly. As the aircraft climbed and air pressure dropped, the aneroid capsule expanded, gradually reducing the spring preload on the flyweight governor. This progressively reduced the target RPM set point, preventing the governor from fighting the supercharger and allowing both systems to work in harmony. The system maintained optimal power delivery from ground level to stratospheric altitude where the air was too thin to breathe. Test pilots reported stable engine operation throughout the climb profile with no pilot intervention required. Set the propeller control once at takeoff and forget it for the entire mission. What breaks first at 30,000 feet? Not the propeller governor. Engineers had designed it to survive conditions more extreme than the airframe could handle, temperatures lower than hydraulic fluid wanted to flow, and air pressures where seals tried to leak into vacuum. It worked because they had imagined every failure and engineered it out. The fundamental principles did not die with piston engines, they evolved. When turboprop development accelerated in the late 1940s as manufacturers sought to harness gas turbine efficiency for propeller-driven aircraft, engineers faced familiar problems with new constraints. A gas turbine core spinning at 15,000 revolutions per minute drove a propeller at 1,200 revolutions per minute through a reduction gearbox. The turbine needed constant revolutions per minute for stable combustion and compressor aerodynamics. The propeller needed variable pitch for efficient thrust generation across the speed range. Different power plant, same fundamental problem, matched the rotating element to the aerodynamic load. The solution was Hamilton Standard's constant speed governor, adapted and refined for new specifications but using identical control logic. Sense engine speed, compare it to the target, modulate blade angle, maintain equilibrium. The feedback loop remained unchanged. Early turboprops like the Vickers Viscount entered service in 1953 and used hydraulic governors mechanically similar to wartime designs, just calibrated for different operating speeds and integrated with turbine engine controls. Later versions added electronic sensors replacing mechanical flyweights and electric actuators replacing hydraulic pistons, but the feedback loop, measure, compare, correct, stayed fundamentally the same. Engineers replacing mechanical components with electronic ones discovered they were implementing the same algorithms in different hardware. Why do old ideas survive new engines? Because good engineering solves principles, not just applications. Change the application, change the power levels, change the operating speeds, and the principle still works. A mechanical governor sensing revolutions per minute with flyweights and controlling pitch with hydraulic pressure is functionally identical to an electronic controller sensing revolutions per minute with Hall effect sensors and controlling pitch with electric motors. Both maintain constant speed through negative feedback. The physics does not care about the implementation details. Today, a Boeing 737 pilot advancing the throttles for takeoff at any airport worldwide never thinks about propeller pitch. The aircraft has turbofan engines, not propellers. But look closely at the massive fan blades visible through the intake cowling. Those airfoils, each one the size of a person and weighing over 50 pounds, operate on principles directly descended from Hamilton Standard's constant speed governor from the 1930s. Variable geometry inlet guide, vanes, and compressor blades controlled by full authority digital engine control computers, sensing engine speed, temperature, and airflow. Adjust their angle of attack continuously to match aerodynamic loading to operating conditions. The feedback loop runs at megahertz clock speeds instead of mechanical flyweight frequencies, and the adjustments happen hundreds of times per second instead of dozens. But the concept is identical. Sense the operating condition, compare it to target, adjust the blade angle, maximize efficiency. Modern military fighters use variable pitch turbine blades that adjust stator angles to optimize thrust across the flight envelope. Helicopters use constant speed rotors with cyclic and collective pitch control that traces directly back to propeller governors from the 1940s. Even wind turbines, those giants generating electrical power from prairie winds, adjust blade pitch automatically to prevent overspeed damage in high winds while maximizing energy capture in light winds. The same fail-safe coarse pitch protection Hamilton Standard engineered in 1939 just applied to electrical generation instead of thrust. Where is the gearbox in the sky now? Everywhere. In every turbine engine, every helicopter, every application where rotating blades must adapt to changing conditions. We just stop noticing it. That is when engineering becomes invisible, when it works so reliably, so consistently, that we forget it exists and take its perfect operation for granted.